Okay, the Cartesian coordinate system is named after a French mathematician and philosopher. Do you know who? Yeah, this was the Latin version of his name. He's more famous by the name of Descartes. I don't know if you've heard of him. You have, good. So René Descartes, and he's responsible for several important things, but maybe the most important one of all is this Cartesian coordinate system. It's the current way, our way of relating things that are purely geometric, okay, with algebra. Okay, so our ability to take a function and draw a graph of the function is this Cartesian coordinate system. And to take an equation and relate it to tools from calculus is through this Cartesian coordinate system. Okay, so, and this is 17th century. So named after René Descartes, the Cartesian coordinate system is the following. The thing that we're going to do now, which maybe you haven't seen a lot, is do it in 3 dimensions. That's the important thing. So here's how we draw a Cartesian coordinate system in 3 dimensions. We're going to need 3 axes, x, y, and z. And the way we usually draw it is like this. And what you should picture here is not a 2-dimensional picture, but rather a 3-dimensional picture. And think of this as like you're looking at the corner of a room. Okay, so in the corner of a room, you look at it from the side, you see this is the floor, right? So the floor is the x and the y axes. And what's the angle here? Here, what's the angle? Right, it's 90 degrees. Do you agree? And this is the wall coming up, or the corner between the 2 walls. And these are all 90-degree angles as well. Clear? Can everybody see this 3-dimensional picture? And it's, for some people, it's more difficult than for others. And it's not, many times it's not something that you can just teach, this 3D ability to picture things. And it just takes time and effort to get used to them. Okay, so we're going to do it slowly, but hopefully everybody will get used to seeing these pictures and understanding them, although they're flat. I can guarantee you this thing is completely flat, but still you should see here something without the glasses. You should see here something 3-dimensional. Okay? So by the way, how do we decide which axis to name what? So the rule in this system is called the right-hand rule. You take your right hand and take your 3 fingers, and if you put them correctly, you should see that they each form 90-degree angles with each other. And I'm going to point them at you. This is x, this is y, and this is z. Okay, so x is pointing at you, just like here. Can you see that x is pointing at, watch out. Do you see that x is pointing exactly at you? Do you see that? Okay, so x is pointing at you, y is pointing there, and z is pointing upwards. Clear? This is the right-hand rule. Okay, now we're going to have specific names for unit vectors in the direction of the axes. So a unit vector in the direction of x is going to be called I hat, because it's a unit vector. Notice that it's a unit vector. It's of length 1 marker. Okay. A unit vector in the direction of y is denoted by j hat, and a unit vector in the direction of z is denoted by k hat. These are standard notations. Okay, I, j, and k. Now the point is that, maybe I'll do it for just a minute in 2 dimensions. If you take, here's good old Cartesian system from Calc 1 in 2 dimensions. If you take a vector, here's a vector, let's draw it starting at the origin, call it A. If you take a vector in 2 dimensions, you can always write it as the sum of 2 vectors, one in the direction of x and the other in the direction of y. So this A is the sum of a vector here in the direction of x, plus, remember how I add vectors, I start one where the other one ends, plus a vector here in the direction of y. Do you agree? Okay, so A is this plus this. I can do the same thing in 3 dimensions. That's what I want to do now. So here's my coordinate system, the 3D Cartesian coordinate system. Here's x, here's y, here's z. And any vector that I take, I can break up into its components. Okay? So the best way I think to picture it is to start not by drawing A, but by drawing a component here, and then adding them. That's how you get A. So that's what I'm going to do. I'm going to take a component on the x-axis. Here it is. This is a vector in the direction of the x-axis. Do you agree? Now I'm going to add to it a vector in the direction of the y-axis, but in order to add it, I'm going to have to start it here. So here goes. Here's a vector in the direction of the y-axis. It's still lying on the floor. Do you see it? Okay. And now I'm going to add to that a vector in the direction of the z-axis. But I'm going to have to start it here in order to add them. Here goes. Okay. So the sum of these 3 vectors, is a vector that starts here and ends where this one ends. It's this vector in red. And note that this vector in red is not on the wall of the board. This vector in red is coming out at you. Do you see that? Okay, because x pulled you out here, so this vector is still coming out at you. Can you understand why I'm doing this and being careful? Everybody? Good? Okay, so how do I express this? I'm going to say that A equals, what's this vector? What's this purple one here? This purple one is some multiple of the unit vector in the direction of x. So this thing is the vector A1, I'm going to call it, times I. Do you agree? Some multiple of the unit vector in the direction of x. This vector is some A2, some scalar, times a unit vector in the direction of y. Do you agree? By the way, what's the angle between these 2 vectors? What's the angle here between these 2? It's 90 degrees. Do you see that? They're on the floor. Everybody good? Okay, here again there's a 90-degree angle. And this third vector here is some other scalar, call it A3, times the unit vector in the direction of z, k. Okay? So any vector A, and you can do the opposite. You can start with the vector A and then break it up into its components. Okay? So in general, let me erase the 2-dimensional picture here. In general, any vector, can be written as a sum of scalar products of I, j, and k. Okay? The professional word for it is a linear combination of I, j, and k. That's the word you're going to use in algebra when you talk about these things. So it's A1 times I plus A2 times j plus A3 times k. And this is true for any vector A in 3 dimensions, in 3D space. Okay? What is the length of A? Can I express the length of A in terms of these components? Okay? In terms of A1, A2, and A3. These are numbers, right? These are the multiples, the scalar multiples of the unit vectors in the direction of the axes. So can I express it? The answer is yes. So the theorem, let's call it a theorem, the length of A equals the square root of the sum of the squares of the components. That's the theorem. I want to prove it. It's a very easy proof. And it's based on the Pythagorean theorem. Okay? This is, in fact, kind of a 3D analog of the Pythagorean theorem. Do you agree? Okay, so let's prove this. Prove. And I'm going to need some labeling here in order to write things down. So I'm going to call this point, well, the origin I'm going to call O. O looks like a 0, so it's a good name. The point where A ends, I'm going to call capital A. That's this point up here. And then this point down here I'm going to call B. And this point here I'm going to call C. So these are just labelings of these 4 points that play a role here. I want to also draw this dotted line here. This is going to be auxiliary for the proof. Okay? And I'm also going to point out that there's one more 90-degree angle here, which doesn't look 90-degree-ish, but this angle here is also 90 degrees. Between this dotted line, which is on the floor, and this thing that's coming up, the angle is 90 degrees. Can you envision that? Do you see that? Everybody? Okay, so maybe I'll erase this. This is the 190-degree angle that's obviously 90 degrees, and it may be confusing. Okay. Do you agree that this angle that I drew there is also 90 degrees? Everybody? Okay, so now the only thing I'm going to use is the Pythagoras theorem. So let's first look at the triangle OCB. This triangle lies completely on the floor, and it's a right triangle. This angle is 90 degrees. Do you agree? So in the triangle OCB, by the Pythagoras theorem, OC squared plus CB squared equals OB squared. Do you agree? Okay, so I'm going to write OB squared is what? Is the length of CB. What's the length of CB? It's precisely A2. Do you agree? Everybody? Okay, so this equals, and what's the length of OC? A1. So OB squared is A1 squared plus A2 squared. Does everybody agree to this? Good? Now let's look at this triangle OBA. This triangle is standing parallel to the floor, not parallel, 90 degrees to the floor. Okay, do you see that? Okay, so in the triangle OBA, again by the Pythagoras theorem, OB squared plus this squared, what's this? What's the length of BA? A3 equals the length of A squared. Do you agree? So we get the length of A squared equals A3 squared plus, or let's write it, OB squared plus A3 squared. OB squared plus A3 squared. Do you agree? Everybody good? Now all we have to do is take OB squared, which we found here, and plug it in here. So the consequence is, let's remove this y-axis, make it a bit shorter. So the conclusion is, you all know this symbol, right? So it follows that A squared equals OB squared, which is A1 squared plus A2 squared, plus A3 squared. And by taking square roots of both sides, you obtain the formula for the length of A. Good? Okay, do you all know this mathematician? What's his name? What's the name of this little black square that you put at the end of a proof, denoting that the proof is complete? It's called Halmos. It's a Swedish mathematician. I think he was Swedish. And he just introduced this. He wrote in some paper, used this black thing instead of writing QED or writing a full sentence, the proof is complete or something like that. And it just, everybody followed. And it's called a Halmos, named after him. And I think he's the, if you take a single mathematician that appears in the most mathematical publications, it would be him. More than all the famous ones like Newton and Leibniz and Cauchy, and right, because he's in every paper until today disregarding of the topic. There's Halmoshes all over the place. What a nice thing, huh? Okay, so now we know how to write a vector as coordinates. So these are called the coordinates of the vector. A1, A2, and A3 are called the coordinates of A. That's what they're called. And now we know how to write a vector in terms of its coordinates and how to find its length in terms of its coordinates. Okay, good. And a remark, sometimes you would find people write, instead of writing A1 times I plus A2 times J plus A3 times K, you will see people write, and we're going to use this notation as well. We're going to use both notations interchangeably. So people write just A1, A2, A3, right? Only the coordinates to indicate the vector. Okay? And if you think of this as a point in three-dimensional space, which point is it? Right, it's the point A. It's the point where the vector ends if you were to draw it starting at the origin. Okay? So sometimes we do this identification of thinking as points in space and vectors as the same thing. And this is a bit sloppy. You have to be careful, because doing that, thinking of the point A, the point A1, A2, A3, that's the point A, right? Identifying it with the vector A is implicitly assuming that A starts at the origin. But remember that if A is here, it's the same vector here, or here, or here, as long as it has the same direction and the same length. Okay? So thinking of writing the vector in terms of its components is fine, because it means this. And remember, I itself does not start at the origin. I is a vector in the direction of x of length 1. Okay? So writing this is completely formal. Writing this is completely formal as well. Identifying the point A1, A2, A3 with the vector A1, A2, A3 hides an implicit assumption that the vector starts at the origin. Good? Clear? Okay. And it's sometimes a bit confused. It sometimes is a bit confusing. That's why I'm mentioning it. Okay, let's do. Well, maybe I'll write some. Let's call it a theorem. It's again some rules, and it requires proof, and the proof is easy. I'm not gonna bother doing it. So if A is the vector A1I plus A2J plus A3K, and we're going to take another vector B, it's going to be B1I plus B2J plus B3K. So these are two vectors written in terms of their coordinates. Then we know what A plus B is. We know how to add vectors. What's going to be your guess as to what the components of A plus B are going to be, the coordinates? Right. So A plus B is going to be the vector A1 plus B1, A1 plus B1 in the I direction, plus A2 plus B2 in the J direction, plus A3 plus B3 in the k direction. Okay? So adding, which was a totally geometric thing, now becomes a totally algebraic thing. Add the components. Okay? And what is m times a? It's ma1 in the I direction plus ma2 in the j direction plus ma, oops, yuck, ma3 in the k direction. So multiplying a vector by 3 is multiplying each component by 3. Okay? I'm not going to formally prove this assertion. You can just draw a little picture. Do it even in 2 dimensions. Don't do 3-dimensional addition of vectors. It becomes a mess. Okay? Do it in 2 dimensions. Take a vector on the board or on your paper, add to it another vector, and try to figure out what the components are and how they add up. Just in the regular XY system. Okay? And see that this in fact holds. Okay, one example, let's start a new board for it. Example, find the coordinates of a vector from the point A, which is going to be the point 1, 2, minus 1, to the point B, which is going to be the point 0, 1, 5. So I'm taking 2 points in 3-dimensional space. I can draw a vector which starts at A and ends in B, right? And now I want to know, what is this vector in terms of coordinates? How do I find its coordinates? And the way to do it, I'm going to solve it abstractly first and then plug in the values. So here's the vector, here's the point A, here's the point B. Just 2 points, not these points, just any 2 points. I can draw a vector connecting them. Do you agree? Okay? Now, how do I find the components, the coordinates of this vector? Here, down here, let's say, here's my origin. Okay, this is the corner of the room. This is where the coordinate system starts. Okay, so this is the XYZ Cartesian coordinate system. I can draw a vector. Let's call this point as before. Let's call it O, the origin. Okay, I can draw a vector from O to A. Saying it is easy. Oh, I even hit A. Good. So this is the vector OA. Do you agree? I can draw a vector from O, from the origin, to B. Here it is. This is OB. And do you agree that OA plus, let's write like this, the vector OA plus the vector AB equals the vector OB? Do you agree to that? Therefore, AB, which is what I'm interested in, is OB minus OA. Do you agree to that? Everybody? Okay. Now, what is OB? OB is a vector that starts at the origin and ends at the point B. So in terms of coordinates, these are the coordinates of the vector OB. Do you agree? Okay. What is OA? OA is a vector that starts at the origin and ends at the point A. So these are its coordinates. So OB minus OA is subtracting these 2 vectors. How do I subtract vectors in terms of coordinates? Using that theorem that we just wrote. Okay, I subtract coordinates. Let's take a look back at this board for a second. Well, I wrote here for addition how we add 2 vectors, but I also know how to multiply a vector by a scalar. And in particular, I can multiply by minus 1, right? So minus A or minus B is just putting minuses on all these. So A plus B, which is the same as A plus minus B, is just subtracting in coordinates. Do you agree? Does everybody see that? Does it make sense? Okay. So back to our board. So Now we can do everything for our example. So in our example, AB equals OB. OB is just this vector. 0i plus 1j plus 5k. That's OB. Minus OA. OA is 1i plus 2j minus 1k. And then I can do them in component-wise, so it's 0 minus 1, so it's negative 1i, 1 minus 2, negative 1j, 5 minus minus 1, plus 6k. That's the vector AB. Okay? Now note that these are the coordinates of AB. If I want to identify AB with the point minus 1, minus 1, 6, that's not going to be exactly this picture, but it's rather going to be the picture of AB starting at the origin. Do you understand what I mean? Okay, what I found is the components of AB as a linear combination, as sums of scalar product of these I, j, and k. Okay, but that's not exactly this picture, because if I think of it as starting at the origin, if I want to say that AB is negative 1, negative 1, 6, okay, and think of the point negative 1, negative 1, 6, it's not B and it's not A. It's a point somewhere here where if I were to start AB at the origin, it would end at the point negative 1, negative 1, 6. Is that clear? Okay, good. What is the length of AB, by the way? Remark. What is the length of AB? I know its components. So what's the length? The square root of the sum of the squares of the components. That's the Pythagoras 3D version. So it's minus 1 squared plus minus 1 squared plus 6 squared. And what's this? 1 plus 1 plus 36, so it's the square root of 38. Clear? Good? Everybody with me? Okay. So, good. Now we know how to work with vectors in their Cartesian representation, writing them with coordinates. And that's going to prove useful. And just a comment, you can define vectors like this. You can define a vector as having 3 components. And then you need to prove that the geometric definition, the geometric point of view, coincides with it. Okay? So what we did is we started with the geometric point of view, and then we showed or stated it as a theorem that everything carries over to this algebraic point of view. You can start vice versa. Okay? But you should agree by this point that these are 2 different takes on the same objects, okay? And we can use them interchangeably. You can, when you feel like it, draw them and add them, and when you feel like it, you can use coordinate systems. And we're going to need both, okay? Sometimes usually the situation is that when we get a problem to tackle or an example, we're going to start with the geometry to figure out what's going on. And then in order to do calculations, we're usually going to resort to the algebraic sides. That's where calculations are more user-friendly. Okay? We don't have to draw things. Good? Okay, so coming up next, after the break, what's called a different kind of product, but now it's going to be a product of 2 vectors, which is going to give a scalar. Okay? And it's called a scalar product after the break.